So today we're going to continue with this discussion. And I'm happy to introduce Stuart Armstrong, who's going to talk about outrunning the law. The ease of intergalactic colonization poses unique challenges for star-spanning civilizations.
Thanks for inviting me to speak here. The British Interplanetary Society is an impressive organization with an even more impressive name. So it's a great pleasure to be here. Now, this talk is going to be a bit larger scale than most of the talks in this conference, both in space and time. It grew out of a project with my colleague Anders Sandberg that's published in Acta Astronautica. We work at the Future of Humanity Institute in Oxford. The emphasis here is, can you outrun the law? In the vastness of the cosmos, who has the advantage? The pursuer or the pursued? Now, our preference for which way round it goes depends critically on who we think is chasing who. We feel quite different from this kind of situation as we do from this kind of situation, or this kind of situation, or again, this one. And the thesis of my talk is going to be quite simple, is that there's an immense first mover advantage, and that it's actually easy, in quotes, to escape and never be caught, no matter who is after you. It's also easy to seed the entire universe with police probes and catch absolutely everyone. And it all depends on who goes first. Let's have a look at these. What do I mean that you can escape and never be caught? Well, this is the Friedmann equation, which governs the long-term fate of the cosmos. And our current best understanding is that we live in a flat universe with a cosmological constant, which means that ultimately the universe will be expanding faster and faster, and ultimately exponentially, as a de Sitter space. What this means is that different points in the universe will expand far away from each other faster and faster until they're expanding faster than light in relative speed, and nothing from one can get to the other. So if you start with enough of an advance and go fast enough, even a light beam sent after you will never manage to catch up. So it doesn't matter what your pursuers do, as long as they can't break the light barrier, they'll never catch up with you. So if you go at a certain fraction of the speed of light, get 5-10 years advance, you will escape. So what about preventing escape? How is that possible? Well, that's a little bit harder. The only real way of preventing escape is to get everywhere first. And most people, when they think of cosmic expansion, sort of think like this. You go from one galaxy, you go to the next, you gather resources, found a new civilization, get independence, and then you have another stage of colonization, and so on. Problem with this is that, for instance, say if you want to get to that galaxy, you may not be able to. Because of all the zigzagging you've done, by the time you get there, you can't cross to that galaxy before it slips away due to the accelerating expansion of the universe. Whereas somebody who is going there directly could get there before you. So if you want to seed police probes, zigzagging around is not the way to go. This is the way to go. Go absolutely everywhere immediately. And if you do that, well, there's no escape. There's going to be an officer waiting for you when you get there. So how easy is it to do this, to expand simultaneously to every single galaxy in the reachable cosmos? Well, let's think about, could we do it? The world comes together in peace and harmony, and with the single goal of seeding the entire universe with probes. Well, possibly worthy goal. Is it possible? The three questions asked are: where are we going to get the energy and the materials for this? What sort of probe are we going to send? And how long is it going to take before we can launch all this? Now, to sort of answer these questions, I'm going to use the methods of exploratory engineering, which is to look at things that could be compatible with known physics and plausible in the future. Here we have schematically, we have the forbidden zones, we have down here what we already can do, and they're trying to find out what could happen in that zone. Of course, the problem is that compatible with known physics is kind of doable. Estimating what's plausible in the future is a bit more tricky. So assume we have a few thousand years, what are we going to see? Robots, butlers and teleporters? So we can't just sort of use our imagination to figure out what's going on. I'm going to be appealing to two principles to guide here. First of all, I'm going to assume that if it's been done in nature, we'll probably be able to do it ourselves at some point, by copying it or by co-opting it. We've done this over and over again. So I'm going to assuming that some level of artificial intelligence is possible through computers, through brains, through whatever, and replicating cells are also going to be possible. The second assumption is that tasks can be automated, including building factory and building construction machinery. Again, this seems perfectly compatible with past trends. We're automating more and more things. And what these means together is that scale, just bigness, is not in itself an insurmountable barrier. The real limiting factors are energy and time. If we have those, we can achieve pretty much anything we want. So, energy. Where can we get that? Well, the old favorite, Dyson structures. Now, there's a few designs of this. There's the Dyson shell, which is the one that that's in many sci-fi books. It's completely impractical. You need materials with unbelievable strength to construct a solid structure. The more realistic one is a Dyson swarm, lots of orbiting collectors. The main problem here is to need organization, so they don't crash into each other or occlude each other. There's also some entertaining ideas like a Dyson bubble, which is sort of a solar captor suspended by the solar wind. For our star, we'd need ultra materials to do this. Not as extreme as a Dyson shell, but still beyond what we can do today. Or we could just do it with a hotter star. Now, we may not have a hotter star to hand, but it's to bear in mind that if there are alien civilizations, they may be around hotter stars and may find these structures easier to build. But let's go with the Dyson swarm. In order to do this, we need a convenient source of materials close to the sun. Well, sorry, Mercury. It's nothing personal. So, Mercury's mass is of the order 10 to the 23 kilograms, or technically known as a lot of stuff. About 50% of the mass is usable, mainly hematite. This is a conservative assumption. Probably far more is usable, but this is what I'm going with. So this is the useful mass of Mercury. And if we made a complete Dyson swarm out of this in Mercury orbit, it would be about 0.5 millimeter in thickness on average. Since a Dyson swarm is mainly just massive amount of reflective surfaces hanging unsupported in space, this is more than ample. So, what's the process? Well, get energy. Use that energy to mine stuff on Mercury. Get that stuff into orbit. Process that stuff into solar captors, which allows us to get energy and continue the cycle. The assumptions I'm going to make is that it takes 5 years to process and position the extracted material. This is probably a massive overestimate. Again, 50% of its material is usable. 1/10 efficiency for moving the material off planet. 1/3 efficiency for the solar captors. Initially, 1 1 square kilogram of solar captures on Mercury's surface to get us all started. The details of the assumptions are not all that important, as we'll see. So what happens under this assumption? Well, this is the amount of power we have on a log scale. For the first 5 years, we have nothing. We're processing the stuff. Then there's a sudden surge as the first generation of solar captors comes online. Then a second surge as the second generation comes online after 10 years. And then it sort of smooths out. I've stopped the graph at 30 or so years. Why have I done that? Well, because the mass of Mercury in that time does that. The key here is the feedback loop that I described, how the energy goes back into the mining that goes into processing the material to make in the factories to get more energy. As I said, the key assumption was that this could all be automated. If you get that exponential feedback, then the details of your assumption doesn't matter. You will take Mercury apart in very reasonable amounts of time. So we've got our energy. What are we going to do with it? We're going to launch the probes. The rocket is pointing in the right direction there because the rocket's only going to be decelerating. We're going to launch it from here using other methods like winch gun, coil guns, rail guns, solar sails with lasers. There's quite a lot of different ways that we could be launching our probes. Now, what would we send? What are these probes? Well, the basic probe is a von Neumann probe, which is a self-replicating probe. It's easier to send a small thing that builds copies of itself than to send it all at once. So this is the most basic design of a von Neumann probe. Take a couple. Take a lot of couples. Get some life support. Give them some data. Put a factory on board. We need an engine. Tie all this together and you've got a von Neumann probe. Not necessarily the best design. It's hundreds of tons. It has limited acceleration, and there's a whole host of social issues that you might need to contend with. What's more realistic design? Well, this is the Bracewell-Freitas self-replicating probe based on the Daedalus design. It's the payload, the actual replicator, weighs about 500 tons. It requires basic AI, which I'm assuming we have anyway. And this is sort of our upper bound on a realistic self-replicating probe. What's the lower bound? Well, this is the Merkel-Freitas molecular assembler. It weighs 10 to the minus 18 kilos. Let's go for 10 to the minus 17 if we add some things to allow it to interact with this environment. This is technically known as very small. But to get realistic numbers, let's turn to nature. We have Vibrio Comma, which is a general environmental replicator at 10 to the minus 16. Slightly larger, there's E. coli, that's a robust replicator. The smallest seed is at 10 to the minus 9 kilos. Now, seeds are interesting because they create macroscopic structures, which is what we want. And the smallest acorn comes in at 1 gram, and an acorn is just a solar-powered factory for producing more acorns that grows huge. This is the kind of thing that we're looking for. Initially, we'll probably make it nuclear-powered, and what it needs is legs, drills, roots to extract resources. Biology has all of these. They can be made tiny, so I'm assuming we can copy that. So my sort of median estimate for how small we can make this probe, including all the things it would need, is 30 grams. So we're going with 30 grams, but remember the 500-ton Freitas probe as an upper bound. Now, you might think there might be data storage limits. How much information can we send on this 30-gram probe? Well, quite a lot, as it turns out. This is what we could, the sort of most compact data storage we could realistically imagine in the future is, say, take diamond with carbon-12 or carbon-13. This is 1 bit for each one. This is of the order of 22 bits per gram. As a comparison, a recent, well, not so recent, but estimate puts all the world's data at 10 to the minus 21 bits. And if you imagine the human brain as mainly being defined by its connection and its synapses, that brings the human brain at about 100 terabytes. So in 1 gram of material, without compressing it anyway, we could put all the world's data and the population of Britain. Of course, we probably won't be using this design, but the theoretical limits on data storage are not going to be a problem for our probes. How are we going to decelerate when we arrive there? Well, there are many exotic ways, buzzard ramjets, gravitational loopings or stuff like that. But let's just be very conventional and let's say we're going to use a rocket. This is the relativistic rocket equation. It is what's technically known as extremely bastardly. Our final mass is 30 grams. And I've got 3 scenarios for deceleration. A very speculative one where we use a matter-antimatter drive, slightly more reasonable one where we use fusion rockets, and a perfectly believable one employing fission rockets, decelerating from speeds of 50% C, 80% C, and 90% C. I'm going to take the diagonal as scenarios to consider. And rounding these up somewhat, I'm going to model probes of mass 5 kilos, 15 tons, and 35 tons. Now, I said that I'm going to ignore alternate methods, but there's one alternate method that I think should be mentioned for decelerating, which is don't bother. Remember what I said about the ever-accelerating expansion of the universe? In practical terms, this robs our probes of velocity as they move further and further out in relative to co-moving coordinates. So if we let it go long enough, they're just going to stop anyway. So especially for the most distant galaxies, it's perfectly possible to aim at them and then just coast in at a practical standstill when you arrive there. So I'm also going to be modeling probes of 1 kilo. Under this assumption. So how far can we get? Solving the Friedmann equations again and the geodesics, this is how far we can get into the universe in current co-moving coordinates at 50%, 80%, 99%, and at C itself. This would allow us to reach slightly over 100 million galaxies at 50% C and slightly over 4 billion galaxies at 99% C. Now, there is another problem. What if we collide with something on the way? At 99% C, even particles of mass 10 to the minus 12 hit with the explosive power of a grenade. The density of such particles is fortunately quite low, but if the probe does hit one, it could go very badly. Now, there's Eric Drexler working at our institute at the moment, and he's come up with many exotic and entertaining ways of shielding the probe. But we'll lay that aside for the moment and just think of redundancy. Just send out enough probe that you have a reasonable chance of getting through anyway. The redundancy we would need is the exponential of dA rho. Rho is the density of particles. D is the distance traveled, which is less than 4.09 megaparsecs. Now, I bet that's not a unit that you get to use very often in casual conversation. The area I'm going to put as 1 centimeter squared. So we're thinking very long and thin. Since this is just its coasting form, this feels perfectly doable. It would obviously deploy into something bigger for deceleration phase. Given those assumptions, we need to send about 30 probes to have a reasonable chance of one getting through. I'll round that up to 40. So 40 at 99% of C. For slower speeds, it's not really a problem. We can send 2 probes just to make sure. So let's put this all together. We have fission engines, fusion engine, antimatter, and no deceleration. They are these at 50, 80, and 99% C, the mass, the kinetic energy, the fuel energy, and also the number of probes that we would send out. The redundancy times the number of galaxies that we could reach. We're sending one per galaxy. That seems the more efficient way of doing it. Total energy for all of these would be of the order 10 to the 30, 10 to the 29. How does that compare with our Dyson shell's output? Well, Dyson swarm's output. Well, here's our sun, 10 to the 26 watts. Assume 1/3 efficiency. How long do you think it would take us to start the colonization of the entire universe, of every galaxy we could ever reach? Well, 30 minutes for fission, 24 minutes for no deceleration, and the worst case scenario is fusion, which would take 6 hours. This is what I meant by easy before. Now, but remember I told you to keep in mind the 500-ton probe as an upper bound. If we sent 500-ton replicators, it would take longer. It would go into the thousands of years, 11,400 years in the worst case. However, all of these numbers on the cosmic scale have an approximation which is 0. And this is about liberty, but this also has some implications for the Fermi Paradox. Because if it's so easy for us to start seeding the universe on tiny timescales in the cosmic sense, it would also be easy for any putative alien species to do the same. So traditionally the Fermi Paradox is the discrepancy between, well, the size and the age of the universe, the speed with which intelligent life could develop and spread, and the lack of evidence for it. So basically, where are all the aliens? Because of the ease of crossing between galaxies, we now need to wonder where are all the aliens on an even larger scale. If we project back into the past, the dotted lines are going back 1 billion years each. This is the number of galaxies that could reach us if they started that many years in the past. And especially if we bear in mind that the Earth is not an ancient planet. There are Earth-like planets all over the Milky Way that are at least 2 billion years older than ourselves. So going back 2 billion years is not a large assumption. And even in the slowest speed, 50% of the speed of light and 2 billion years in the past, there's at least 2.5 million galaxies that could reach us. That's 1 million trillion stars. In my feeling is that the Fermi Paradox just got a lot worse there. Now, there's other reasons to expand. I don't want to go into them in detail, but just mention them in passing. We've covered that there might be some subgroups that might want to expand. We've covered that there might be some who want to escape. And we've covered the police ones who want to stop this expansion or this escape. But other reasons to expand could include that it makes you safe from internal civilization collapse. When you're spread across several galaxies, you're kind of okay. And lastly, this might be the most important one of all, that there's kind of a prisoner's dilemma. We might be okay not grabbing the universe, but we're probably not okay with another alien species grabbing it and doing whatever they want to do with it, which might be used against us. So the best way of stopping some other alien species from grabbing the universe is to grab it ourselves. And you know you can't trust them because they're going to try and grab the universe first because they think we'll try to grab the universe first, the suspicious bastards, so we better grab the universe first. But anyway, as a conclusion, there's a huge first mover advantage. If you want to escape, do it soon. If you want to stop people escaping do it soon. But if we survive, which is a very debatable assumption, and if there are no aliens out there, which is another debatable assumption, then a human group will likely paint the cosmos in their color, the entire cosmos. And the question is, which colors will those be? Thank you.